So here's our first example problem of executing this problem area. So this is example 3 from the first page of our notes. And again, you have to recognize that there's something strange about this integral. And at least this one is quite obvious, I think, because you see that infinity, you're going to recognize, well, that's weird. I never did that in Calc 1. How am I going to sort of proceed from here? So I'm going to have to address that problem. And how I address that problem, remember that your definite integral that we're working on here, we're really kind of thinking about the definite integrals as being from a to b of some function f of x dx. So my problem is with the upper limit of integration. I'm going to call that b, because that's normally what we do back from Calc 1. So my first job is to write a limit on your paper. That's what I mean when I say address the problem. Recognize that infinity is a violation of the fundamental theorem of calculus. I am going to handle that by saying I am going to make b approach infinity, and I am going to keep my integral exactly the same as it was. I'm just going to, instead of writing infinity, I'm going to write a b. So it's a way of tricking it out. I clearly see that infinity is there. I know that that is a problem. But it's almost like you're covering it up. You're saying, well, let's make that upper limit integration some value b, some variable, some unknown quantity, instead of actually saying what it is, which is infinity. What I'm also going to do is rewrite 1 over x squared as x to the negative 2. That's going to help me evaluate this integral. Now again, your job right now is to really hone in on this integral that you're going to actually execute and find the antiderivative. You're going to pretend like there's nothing wrong with this at all. You're going to add 1 to your exponent, divide by my new exponent, and evaluate that thing from b to 2. Now, dragging along in this whole process is that limit idea. You're kind of laying that on the back burner for now because your point here is to actually come up with the antiderivative. So this is just a tag along. It's kind of like a third wheel. It's just along for the ride. What I'm going to do is I'm going to switch over here and just kind of rewrite this. I'm going to rewrite this as negative 1 over x. I feel like that's easier for me when I eventually go to evaluating the fundamental theorem of calculus here. So again, this limit notation just drags along this whole process, but you're really pretending like everything is fine and there's no problem anywhere. You are going to replace b for x in your antiderivative, and then you're going to have minus negative 1/2. That's what your fundamental theorem of calculus says to do. Plug in your upper limit of integration and then your lower limit of integration. So I did that, right? So what I end up with is negative 1 over b plus 1/2. Now remember, hanging out in the background is this issue of limit as b goes to infinity. You have exhausted everything you needed to do for the fundamental theorem of calculus. It's right here at this moment that your work actually does turn out to be a limit question. So I always view these in 3 pieces. This is the last leg of the puzzle. Let's just look at this at face value and see what is happening on this particular guy. So I have the limit as b goes to infinity. So imagine b going to infinity, getting bigger and bigger and bigger, like 10, 100, 1,000. Negative 1 over something going to infinity is just going to 0. We know that from basic Calc 1. So I can evaluate this. I know that that first idea tends towards 0. And then as b goes to infinity, I just have this 1/2. There's no variable in it at all. So just plus 1/2. So what I now realize here is that this integral that I was just kind of working on and working really hard to come up with, it actually equals 1/2. So I now know what to say about this integral for example 3. What I'm going to say is I am going to say, these 3 dots means therefore, this integral converges to the value of 1/2. Okay? We don't want to say that the integral equals 1/2, it's converging to 1/2. Okay. So again, there's 3 pieces to evaluating an improper integral. Step 1 is address the problem, and that means you need a limit in your work. Step 2 is actually evaluating that definite integral using the fundamental theorem of calculus. And step 3 is working out that limit process and coming up with a value. Or not, because it might work out to be infinity. But it's a 3-part process, and each one is really important. I will tell you this, if you do not address the problem, you do not earn points for this problem. If you sort of ignore the fact that the infinity is there, you have not successfully worked out an improper integral. All right, let's move on to example 4. And we're going to handle this particular problem, which has a different issue, right? This is one where, again, I have this function, 1 over x squared. I know that there's a discontinuity at x equals 0, and that's exactly one of my limits of integration. So this is a problem, and I'm going to have to address that problem. And that is, number 1, your first issue. I have to address that there is a clear problem at 0. Now, I'm going to refer to that problem as being A, because your lower limit of integration is usually A. So I'm going to rewrite this integral, and I'm going to go from A to 3. You actually earn some good points there. You've recognized that it's improper, and you've almost successfully dealt with this. And here's what I mean by almost. When you think about it, you're integrating from 0 to 3, right? And 0 is your lower limit of integration. That's where you have a problem. That's where you have your discontinuity, right? So really, if I'm approaching 0, if I'm going to let a equals 0 or a tend to 0, I'm really doing that from the right-hand side. So I'm going to add a little something here. I don't want to freak anybody out, but I'm going to add a plus sign. Because you're letting a, basically imagine it being like 2 and then 1 and then 1/2. You're letting it approach 0, but from values larger than 0. That's what I mean by putting the little plus sign on there. Okay, so this is now perfectly set up to have addressed your problem. 0 is your discontinuity. You're basically covering up the problem. You know that lower limit of integration is 0, but you're going to call it a, and then you're going to take the limit as a goes to 0 from the right-hand side. So that's going to be what we say in the beginning, and that's going to come into play when I finally answer the question. But right now, all your eggs are in one basket here of trying to evaluate this integral, technically using the fundamental theorem of calculus. I'm going to try to evaluate that. And again, I'm going to switch to a -2 exponent because that allows me to use the power rule really effectively. Now, I don't want to miss the fact that there is still a limit on the outside. And I'm just kind of dragging that through the problem. I know a lot of people don't like to write it all the time, but you can kind of tell my perspective is you should always write it. Now, what I want to do from here is actually come up with the antiderivative, which is add 1 to the exponent, divide by your new exponent, and then we're going to force the fundamental theorem on this. We're just doing so with that lower limit of integration being a variable a. So I'm going to rewrite that because I would rather not deal with negative exponents. It's just friendlier for me. You can do whatever you're comfortable with. But here's where I'm going to evaluate this. I'm going to throw the 3 in, -1/3, and then minus, well, then it's going to be -1/a. So what I'm really ending up here with at the end, I've pretty much exhausted all of my work with the fundamental theorem of calculus, but what I have ended up with here is I've ended up with, let me just switch back colors, -1/3 plus 1/a. Now, let's be careful and realize that a is going to 0. Well, there's no a here, so I just have an evaluation to say, well, that's just negative 1/3. There's no variable, so it's just negative 1/3. But here I have something interesting. I have 1 over a tending to 0. That denominator is tending towards 0. I'm just going to kind of write it like that. So let's think about that. You have 1 over 1, or 1 over a half, 1 over 1/3, 1 over 1/4, 1 over 1 over 100. This is really tending toward infinity. So I've evaluated this, right? And I end up with this statement. I have negative 1/3 plus infinity. And look, there's nothing that negative 1/3 is going to do to stop this train wreck of infinity. That doesn't really slow down infinity at all. This limit is infinity. And that is not a number that you can plot on a number line. Basically, you've just decided that your limit does not exist. Because remember, anytime you ever answer infinity, you're actually, embedding in there like, hey, I'm being very descriptive on how it doesn't exist. It doesn't exist because it's going to infinity. So I have to come up with a punchline for how do I answer this question then? Well, you have all of your work here to support what you're going to say. You're going to say that this integral diverges. There's no other way around it. There is no fixed number for the value of this improper integral. And this is very interesting because, you have a similar function. It's the same function. You're just looking at it from some different perspectives. So let me just draw something here and let's discuss a little bit what's going on. So I'm going to draw the graph of 1 over x squared. So it kind of looks like this. Maybe it's more dramatic, right? But we have this issue where we took the integral from, what did we do? 2 to infinity. So I'm just going to make up where 2 is. Let's say that's 2. And we kind of looked at this in terms of what's the area underneath that function from 2 to infinity. That's an infinite region there. That is going to keep on trucking to infinity. And what's interesting is that the area under that function from 2 trucking all the way to infinity actually has a fixed value that it's approaching. That area is approaching the value of 1/2. And that's pretty wild that you have an infinite region, but yet it's approaching a finite value in area. On the flip side, the second question over here was talking about a different problem where you were going from 0, right? Here's x equals 0, all the way to 3. Well, that's a different issue, right? It's still an infinite section, right? If I just shade along what's happening here, this is not closed. This is an infinite region because there's a vertical asymptote there. It's never actually going to close. So this is another infinite region. And this infinite region from 0 to 3, we've actually shown has no value that it's approaching. It really is too big to quantify, and it is diverging. The area is going to infinity. So it's interesting that we have 2 different infinite regions where one converges and one diverges.